Hello and welcome to this first lecture of a new section on solving the game in this course, Mastering Game Theory. So in this section, we will take you through an in-depth view of how to solve the game, a situation that you are in. And in this particular lecture, you will learn how to use backward induction in sequential games to find out the right strategy, optimal strategy, by analyzing the game from end to beginning. So there are two methodologies for determining optimal strategies, and in this lecture we will take a look at this backward induction or working backwards to determine the best strategy, optimal strategy. Let's take a look at how to do that. Any thoughts? How would you do that? Okay, so the backward induction is a method used to solve sequential games, right? Sequential game. And there you analyze the game from end to the beginning. You work backwards, and that's why it's called backward integration. And what are the various steps you need to take? Take a look at that. So, in this example, let's walk through this also. There is a wolf 1, there is a wolf 2. Both have two options, hunt deer, hunt rabbit. And there are payoffs for wolf 1 and wolf 2 as you see here. So if you were to solve this game using backward integration, what do? You start with the end of the game. Now this is the end of the game. Start from the last decision point. The first decision point is at for wolf 1 and the wolf 2 has the next and the last decision point. So you start with the last decision point nodes in the game tree where players make their final choices. So wolf 2 makes the final choice, so that's the end of the game. Then you determine payoffs at the end node. So evaluate the payoffs for all possible actions that you see here at the final decision points. So wolf 2 has four options: hunt deer, hunt deer, hunt rabbit, given the decisions taken by wolf 1, and there are payoffs for both of them as you see here. Then you start coming to choosing an optimal action at the final decision. So you say for wolf 2, what are the optimal decision? That's a final decision to make. So for the final player making the decision in the end node, select the action that maximizes their payoff. And these choices determine optimal strategies at these nodes. So let's see how do you do that. So wolf 2 has two choices of hunting deer and rabbit. If the wolf 1 hunts deer, and there you see his wolf 2's optimal choice is to hunt the deer between the two because he makes it a better choice of payoff of 10 versus in 8. So wolf 2 has better payoff there. Similarly, for if wolf 1 hunts a rabbit, between the choices of hunting deer and rabbit, wolf 2 has a choice of the better strategy is to hunt a rabbit, right? So because the payoff there is higher at 6. Then you move to the previous decision nodes, right? So once the optimal decision for final nodes are determined, then you move to the decision nodes just before that. That's the wolf 1 here. At each of these nodes, you consider, there's only one in this case now. So but if there are multiple, at each of these nodes, you consider the optimal decision already made for the subsequent nodes. So what are the optimal decisions made here? At wolf 2 is to hunt the deer in case wolf 1 hunts deer, and hunt the deer again, hunt the rabbit if the wolf 1 hunts the rabbit. Then what you do is you determine the payoffs considering future moves. So for each action in this earlier nodes, which is for wolf 1 here, you calculate the resulting payoff by considering the optimal actions determined in the subsequent steps. So subsequent steps, the optimal for wolf 2 was hunting a deer, and for that you say, okay, if since the best thing for wolf 2 is to hunt a deer, so that, and if wolf 2 for if wolf 1 hunts a rabbit, these are the two payoffs, and between the two you say which is the optimal point, and wolf 1 as you see here makes a better payoff, gets a better payoff by hunting the deer because he gets a 10 versus 6 between the two strategies, so that hunting a deer becomes a choice for wolf 1. and that becomes the optimal path as you see here. Then you repeat this process moving backwards through the game tree, node by node, determining the optimal actions at each step based on the actions and payoff already analyzed in the future decisions. So you roll back from the future, and then you ultimately you reach the initial decision point, and by this point you would have determined the optimal action for all future moves, allowing you to choose the optimal strategy from the very beginning of the game. Right? You get an idea? Great. Let's take a look at another case of backward induction. In this case, let's consider a simple sequential game with two players, player 1 and player 2. And the game is like this. The player 1's turn, player 1 can choose to play either A or B. And once after that, the player 2's turn comes. If player 1 chooses A, player 2 can choose X and Y. And if player 1 chooses B, the game ends with the immediate specific payoff of 1 and 2 here. And the payoff matrix, as you see here now, partly is that if the player 1 chooses A and player 2 chooses X, the payoffs are 2 and 3. And if player 1 chooses A and player 2 chooses X, the payoffs are 0 and 1. And as you saw earlier, player 1 chooses B, the payoffs are 1 and 2. 1 standing for player 1, 2 the first part of the payoff data belonging to player 1 and second belonging to player 2. That's the convention. So that's a scenario. Now let's do step by step backward induction. So player 2's decision, let's start with the last player's decision because that's the furthermost. So player 2's decision again depends on what player 1 does. If player 1 chooses A, now the player 2 chooses X, the payoffs are 2 and 3, and if player 2 chooses Y, payoffs are 0 and 1. So what will player 2 choose? Obviously X, because 3 is greater than 1 and player 2 will prefer a payoff of 3 over 1, and hence player 2 chooses takes an action of 2 with a payoff 2 of 3. 2 for player 1 and 3 for player 2. Now it is time for player 1 to consider the decisions. So let's look at player 1's decision. And in player 1's, if player, so that becomes the payoff for player 2. You know, player 2 chooses the X because of the higher payoff between 2 and 2, 3 and 0, 1. Now player 1 chooses time for player 1's decision. Now if player 1 chooses A, then knowing that player 2 will always choose X, the payoffs are 2, 2 and 3, 3 for player 2 and 2 for player 1. And if player 1 chooses B, the player of 1. So for player 1, the payoff is higher in case he chooses A, right? So that becomes the choice of player 1. So player 1 will choose A and player 2 will choose X, given that they're both rational decision maker. And that's how you use backward induction to determine the optimal path. So thus the optimal strategies using backward induction are player 1 chooses A, player 2 chooses X, given that player 1 is choosing A, and the payoffs are 2 and 3 for player 1 and 2. This backward induction process ensures that both players make optimal decisions at every stage of the game, right? Right. So what do we do next? So we will look at the another methodology of iteratively eliminating dominant state strategies in the next lecture to figure out the optimal strategies in case of a game. So thank you so much for watching this first lecture of the game of solving the game series in this course Master in Game Theory. I hope you continue to learn new things, continue to enjoy, and I do look forward to see you again in the next lecture. Please feel free to message me if you have any questions. I'll be happy to answer your question, and also download the PDF file to take a look at anything that you need to.